this lesson, we're going to focus on counting gas particles. And so we are still going to use the ideal gas equation PV equals nRT. The n in this equation refers to the total moles of particles in a sample of gas. Okay, when we say gas particle, that's our generic way of referring to each molecule, which are bonded atoms, or a free atom in a gas sample. In other words, instead of saying atom or molecule, we're just going to say a particle. Okay, so a free atom, an atom that's not bonded to any other atom, will count as one particle. A molecule, regardless of how many atoms it has, will also count as just one particle. So if you were to compare 1 mole of methane, for example, versus 1 mole of helium, then n equals 1 in both cases. 1 mole to be more specific. Okay, so it doesn't matter that methane has 5 atoms in it. All right. How do you measure the number of moles of particles? Like I said, we use the ideal gas equation. So what the information you need then would be the pressure of the gas, the volume of the gas, and the temperature of the gas. Because if you rearrange this equation right here to solve for n, what do you get? N equals, so I divide both sides by RT, n equals PV over RT. So if you know the pressure, you know the volume, you know the temperature, you can solve for n. R here is just a constant. It's known as the universal gas constant. And the value of R depends on what unit you're using for your pressure, volume, and temperature. So if you're using liter for your volume, atmosphere for your pressure, and Kelvin for your temperature, then the unit for R, the value of R is 0.08206 liter times atmosphere per mole per Kelvin. Or you can write that as liters times atmosphere over mole times Kelvin. That's another way of writing that unit. Okay, so this is a good number to memorize because you're going to encounter that number a lot. So, and like I said, the ideal gas equation, as we've said in previous lesson, there's a reason it's called ideal, and the reason is that, strictly speaking, it's valid only as pressure approaches 0. Under ordinary conditions, you might at the most be around 1% in error by about 1%. So that's a pretty good equation to use. Okay, so let's look at an example. How many moles of gas particles would you have in a 22-point-liter sample at STP? The abbreviation STP stands for standard temperature and pressure, so you need to know that definition. Standard temperature is 273 Kelvin. That's the freezing point of water, 0 degrees Celsius, and standard pressure is 1 atmosphere. Okay, so let's see if we can calculate the moles of gas particles that you would have in a 22.4-liter sample at STP. Remember, we said PV equals nRT, and so if we solve for n, we divide both sides by RT. Oops. So n is PV over RT. So our pressure at STP is 1 atmosphere. We treat that as an exact number since we're defining that as STP. Okay, so it's a standard value. So volume is 22.4 liters, and our R is, if you recall, 0.08206 liters times atmosphere per mole per Kelvin. That's your R, and your temperature. At STP, the temperature is 273.15 Kelvin. Okay, so let's look at our units here. Atmosphere cancels out, liter cancels out, Kelvin cancels out. You have per mole in the denominator, so you bring that up to the numerator. Your final answer should have moles. Okay, and if we did that, let's go ahead and calculate that. You have 22.4 divided by 0.08206 divided by 273.15, and you get 0.999. Okay, and so that's basically 1 mole. Okay, 1.0, or you can say 1.00 mole if you want. Please take things. So in other words, the volume of 1 mole of an ideal gas at STP is 22.4. So that's a very good conversion factor, actually. 1 mole at, is equal to 22.4 liters. But you have to remember that this, you can use this conversion factor from moles to liters only if you're at STP. Okay? If your gas is at a different temperature and pressure, obviously you know that the volume's not gonna be 22.4 liters.